electrical mentor on Team Shockwave 4488 from Glencoe High School. And I'm here today to talk about 3D printing basics with a spin toward robotics, FRC or FTC applicable. This is a basics of 3D printing. It's not going to be super advanced, so if you have a lot of experience with 3D printing, it may not be quite as appropriate, but it does have a lot of FRC spin, FTC robotics usages, and it does have some more advanced stuff, so it could be useful. I'll let you be the judge. So really, for 3D printing and robotics, all you have to do, download a design from the web, print it out, right? Well, not quite. Really, the things we're going to talk about today, we're going to talk about what is 3D printing and some of the basics of the different kinds of printers that are out there and what you might see or use on your team. Then some tips for designing for 3D printing. There's different things you might want to do to design something specifically to be 3D printed. Then talk about materials that you can use, the different properties of those materials, which ones have what strengths, that sort of thing, and some of the pitfalls that we as a team have run into using 3D printing on our robotics. And then finally, a whole bunch of different usage cases and places where we've found 3D printing to be useful for robotics. So to start off with, let's cover what is 3D printing, just in general. So here I'm sure you've got some experience with mills and lathes, and these are kind of generally known as subtractive manufacturing, I guess. It's where you start off with a block of something or a rod, and then you take chips off of it and all this scrap material, you pull it all away until you produce some object after chiseling away all of these bits. But with 3D printing, it's really an additive manufacturing technique. It's more like Legos, right? You build it up with multiple Legos and you put it up to stack it up together to get an object. So there's a bunch of different types of 3D printing of this using additive cases. There's SLA, as it's referred to, which is like short for stereolithography, and that is where they use a light-sensitive resin. And then they expose light to it layer by layer and build it up. So the plate, this is this one up here, this plate goes into and dips into a thin layer of that resin. The light exposes the resin and hardens it in certain places, and then the plate goes up a little bit, and then it just keeps going up and exposing more layers until you can build an object something like this. Then there's selective laser sintering, or SLS, and that is this big, huge machine. It's a very industrial usage case. You can do metal powders, titanium, things like that. It's a very expensive process, but it's really cool, and it comes up with some really nice parts. So it's used for, small manufacturing runs like hypercars or that sort of thing, where they're only going to make, 50 of them or something, and you make a fancy intake out of titanium or some fancy metals. And I'd love to get into that if but you have to have a lot of money to buy one of those machines. And then you have the normal things that you see as the 3D printing, which is fused deposition modeling, or FDM. And that's where you extrude plastic out, like what you normally see. So really, to get into a little more details and just show you how to think of FDM printing, it's really like a computer-controlled hot glue gun. And you can see somebody found these pictures on the web somewhere, and somebody actually took the tip off of a hot glue gun and hooked it up to a bunch of stepper motors and put tubes, the rods of hot glue, and managed to force it out through the tip from the hot glue gun and be able to print a little cube like this on their homemade 3D printer out of a hot glue gun. Kind of fun, I think, as an interesting project to see if you could do it. It's clearly not going to be your super accurate and great, usage plastic, but interesting. So there's a bunch of different types of FDM printers. Most of them that you'll see are Cartesian style, where you have like an X, Y, and Z coordinate system that moves the print head around. But there are some that this is like a delta printer that has 3 different points on it, and then this little 4-bar setup, so it keeps your print head flat and then can move it all over the place. But you have to have a combination of movements of all 3 of these motors on each corner. There's also a new one that people have been playing with. It's called a Core XY, which is kind of like a Cartesian, but it has like a differential motor movement. I don't know that much about, but It's kind of an interesting new up-and-coming one. So the key to know about how FDM printers really work, and generally additive manufacturing for the most part, is that it stacks things by layers. So just like weaving here, you're seeing on this, weaving here, you've got on a loom, you build up each layer at a time, and you can build, this one isn't really much of a picture, but you can build tapestries and things where you can kind of stack things together, and based on what color you're using, you can end up with a cool picture and things. And it's the same kind of thing in 3D printing. It's all about the layers, sort of like ogres, very much about the layers. Okay, that's probably a pretty old joke. I don't know. I'm hoping you've all seen the movie. But so some of the interesting advantages to 3D printing is that it allows you to produce things without as much waste material. So when you're using like a mill, right, you start with a block and then you chip away a bunch of stuff, and that just becomes all this waste material. With 3D printing, when you print it, you only use the material that you actually use in the end part. That's kind of a cool advantage. The other thing that is an interesting advantage of additive manufacturing is how you can build things that you couldn't otherwise manufacture. So this is an example of one of the items that I've seen. It's a common one that people have printed. It's kind of a demo model and stuff because it is such an interesting thing. This one is it's called a geared bearing, I guess, and but it's really a herringbone gears. So you've got gear teeth that go this way, and then at the bottom they angle the other way. You can see that a little bit in some of these places right here. You can see how it goes this way and this way. But that means that all of these planetary gears, you can't really put the planetary and the sun gear together in there after you built them. So if you built each one of these pieces separately and then tried to put them together, you couldn't, because there's just no way to assemble it. So really the only way to build this is to print it out layer by layer. So it's a kind of a print in place thing. Anyway, that's kind of a neat advantage for the additive manufacturing. So as I was saying, layers are one of the most important pieces for the FDM style printing. And so one of the key pieces for the process is a slicing tool. So it's a software tool that takes an object that you designed somewhere. We'll talk about the CAD tools for that a little bit later. And it slices it into these layers. So you can kind of see here, this is a nice little Kirby model, and you can kind of see how it's sliced into all these little layers. And there's a bunch of settings and tweaks and tuning that you can do to it, but this is kind of a slicer. And one of the interesting aspects of 3D printing and slicing is that you can put in, instead of having it just be solid plastic, right, you can save a whole lot of material and actually add strength by putting in infill. So there's different sizes and shapes of infill that you can put in, and it gives you different strength properties, but it also uses more or less plastic as in your printing. So you can do this all part of the slicer, and then it produces that G code, which runs on the printer. So as far as options for what slicer to use, there's often you use a brand specific stuff. So MakerBot, if you have a MakerBot printer, it's pretty specific to, they have their own slicing tool. Zortrax has this thing called Z Suite. Zortrax is the printer that our team uses. We have one printer. Up has their own tool. Bunch of different companies have their own tool. Then there's the open source-ish, I called it, because they mostly, there's a set of them that started open source, but then they were usually adopted or pulled in by a particular company to do a lot of the uptake on it. They're still considered open source, but one company is doing a lot of the production work and advancements, and that's like Slicer. Originally, it was a fully open source, and then Prusa started adding a whole bunch of stuff to it. It's still open source, but then they were adding so much that they decided to just go ahead and make their own branch of it. So they have their own branch they call Prusa Slicer, but you can see it's basically the same logo still. They just added their own colors. Cura is still open source, but it's mostly updated and kept by Ultimaker. These are the two main ones I see people use, is the Slicer or Prusa Slicer and Cura. And those are some of the more powerful ones. There are a couple other options, but these are the big ones. So now let's talk about some of the tips for designing for 3D printing. You know, why would you want to design specifically to 3D print? Why don't you just CAD the part and then you can print it or whatever you want to do? Well, there's some certain things you have to consider with 3D printing and FDM specifically, and that is that most of it is gravity works, right? You can see here you're printing out here kind of overhang and there's just nothing there, and as it goes up and does layer by layer, you get out here and it just sort of droops down here, and if you get too much of this kind of stuff, you end up with this huge pile of spaghetti. It just makes a mess and it doesn't really work very well. However, you can do things, this is called bridging. So if you had an attachment point on the other side, you can bridge across it and it can work okay, especially if you have a well-tuned printer and a part cooling fan and some other things. And you can see for short distances, it actually looks pretty good way over there. But the longer distances, it starts drooping some, and maybe depending on what you can do, you can cut away some of this and maybe it's good enough. But when you get really long, that just, I don't know, that would be really hard to use this one. It's still pretty good for a printer because it is just molten plastic and gravity wants to pull it down. But it's something you have to consider when you're trying to design for 3D printing. So support material is an option. So if you want to do something where sometimes you just have to use support material. This part here is if this is like the part that you need, there's really no option because you can't like orient it a different way, you can't position it differently or whatever, and assuming you can't change the design, you're just going to have to put in support material. So in this case, they chose to put support material down in the middle, and then it was able to be cleaned up, and it actually looks pretty good in the end. So support material can work for you, but other times it can actually end up being a disaster. So poor Mario here had a bunch of support material, and it sometimes just doesn't come off well. It depends on your printer, your tuning, your settings, the plastic that you're using, other things like that. It can be really difficult to get support material to come off cleanly sometimes. Now, one of the options that some people use, I've never actually tried this myself, but there is water-soluble filament available. So if you have like a dual extruder printer, or maybe one that can handle multiple colors, in that kind of case, you can maybe use one of the extruders or one of the colors to be this water-soluble stuff that you can kind of see over here on this side, and then you dump it in a bucket of water, and then it removes the water-soluble support material, and then you get this nice thing. The downside here is that water-soluble support material is actually, it absorbs water a lot. So if it's just sitting on a shelf somewhere, it's going to absorb a lot of water. So you have to keep it in a dry box. You probably actually need to actively stick it in an oven or some kind of a drying mechanism, a dryer, to get it back to usable grade before you use it. And it's very expensive. So for those kinds of reasons, I've never really messed with it. Another technique I've heard of just recently is that different types of plastic can be used. So for example, a lot of people have tried using PETG for the support material and PLA for their main object, and apparently because they're just dissimilar plastics, they don't stick together well. It'll be adequate for support, but then it just breaks away really easily because they don't have any adhesion properties. So I haven't tried that myself, but it may be another option that's better, less expensive. PETG is relatively inexpensive, so it's less expensive and it could still work fairly well without all of the problems of the water soluble. I don't know. I haven't tried it. You can let me know if you find success with that. So other techniques that you might want to use to avoid adding support. So for example, let's just say you have this part here that you want to print out. Maybe it's like some kind of an amber light mount thingy for your robot or something. You cut it up and you stick it in the slicer and you're like, hey, slice it. Oh, it needs support. Here's support. That's a lot of support, and it may end up being very difficult to remove. So there are different techniques. The first one to think about is position it differently, right? So if you can tilt it, now you avoid a lot of the support. You still need some support for these forks up here, or for one of the forks, but this is a lot less, so it's going to be simpler to get the support material off. The other thing to note with changing the orientation is you get different strength properties. So the way the grain of the layers go gives you different strength properties, and we'll talk about that a little bit later. But there's also another option for trying to get rid of the support material, and that is to change the design a little bit. So possibly if it would work in adding this kind of a support, which I think it actually would, if it was an amber light mount, it probably wouldn't work, but depending on what you're actually trying to do, this may be sufficient, and you can just add a 45-degree angle down here and turn this whole thing into, so there's no longer any big overhangs, there's just this 45-degree angle, and most printers can handle 45 pretty easily on a print. So this should print pretty reasonably. Now whether you can do this to your part or not, it depends. But that's an option. So that's something to think about as you're designing a part. If you know you're going to 3D print it, you want to try to figure out what you can do to avoid the requirement of support material. So CAD tools. Virtually any CAD tool our team uses Inventor, but I know I've also used Fusion 360 and other things. So CAD tools always have some way to export your design as an STL file, and that's really what you want for 3D printing, to go into your slicer when you want an STL file. So, but the key that I want to remind people about here is that when you do it, you need to find the options from your CAD tool, because probably your team is using inches in your CAD tool, and so if you take a design that was in inches and then you export it as an STL, it's not going to work well on your printer, because all slicers and all printers that I've ever heard of work in millimeters. So they assume the numbers that they're getting, the dimensions of things, are all in millimeters. So when you do export as an STL, you want to open up whatever that option setting is and make sure to check millimeters, and you want high resolution. That with those settings, then you can actually get it. If you don't select the millimeters and it exports as inches, you're going to have to do some kind of weird scaling, like 25.4x scaling or something like that, because it's going to, the slicer is going to interpret the numbers as millimeters, but they're actually going to be inches. It gets really confusing. So make sure you export in millimeters. Another great CAD tool that I use and that our team uses is OpenSCAD. Now, OpenSCAD is like a little bit weird. It's not a normal CAD tool. It's actually a scripting language. So it's more like your Python or your C shells or whatever, you know, those kinds of scripting languages. But instead of scripting to run routines and run executables and things like that, it actually describes a three-dimensional object. So you can see here, I actually did a really quick script here that describes the logo for OpenSCAD. This is their logo, and it's really just a, you know, this first line you create a sphere, then you create some cylinders and you poke holes through them. You subtract cylinders through there and it pokes holes through it, and you get this cool little design. So it can be very powerful in ways to describe the three-dimensional objects, and it still exports as STL, just like all the other CAD tools. It can be really powerful. Excuse me. One of the best things about OpenSCAD is the libraries that are available. So there's a whole bunch of really powerful libraries that you can download off the web that people put out there for free, which allow you to match threads, which can be iffy success, or gears, which sometimes you don't have the strength in the plastic to really be able to do a lot of gears, because there's not a lot of teeth that mesh when you do that. You just have a couple of teeth that take all the force of gears, but it can work if you need to. But the one that we use most often on our team is pulleys. So there's a pulley library that you can get, and then you can just give it, you know, number of teeth, dimensions, pitch, what the type of belt is that you're running. You know, there's HTD5 or GT2 3mm pitch or whatever. All those different options, you can set it as parameters over here, and it'll spit out different size pulleys with different holes in it and things like that for the different kind of shaft. And then you can 3D print this, and it actually turns out really well. And because of the way belts work, belts distribute the forces across, you know, a whole, you know, usually around half of the circle. You get it spread across a lot of the teeth on the pulley, and you actually can distribute the forces really well. So especially if you can print in some harder materials, some nylons or some polycarbs or things like that, this can be a really good solution. All right, that leads us into materials. So let's talk about the different materials that you can get for your 3D printer, and for FDM's printer specifically, and what those kinds of things are. There's a list of them here. There's of course a whole bunch more. They keep adding new ones, but the most common ones are PLA, ADS, PETG is getting to be more common now, and then The flexible one is TPU. Nylons and polycarbs are kind of into your higher strength. They're a little more complicated to print, but higher strength materials that you might want to consider. Then if you want to look at why would I pick different kinds of plastics, you can find charts like this which kind of give you a comparison of different properties of the different kinds of plastics. So you can see here you got all these different types of plastics or different colors on here, and it puts it into a scale for ease of printing, quality, that sort of thing. I want to point out specifically that max stress and impact resistance are kind of two different versions of strength. So max stress is just static strength. So if you grab a piece and try to break it this way, you kind of get your max stress. But impact resistance is when you like smash it with a hammer or you run into it with a robot, for example. And you can see that the different kinds of plastic have different properties here. So for example, the max stress PLA actually comes out really good. It's actually really quite strong, but it has poor impact resistance. So it may be strong, but if it gets impacted, it's not going to have any kind of give to it. It doesn't have any little flexibility. It's very brittle. And so there's some interesting property trade-offs there that you want to consider. There's a bunch of new things that people are coming up with. So there's carbon fiber infused. So one of the really popular printers that people are using on a lot of FRC teams now is Markforged. And those are great printers. They're a little expensive, so we don't have one, but Markforged makes some really great printers, and their main material is called Onyx. And that is a carbon and fiber infused nylon, and that is actually a very good material. There's some other ones you can get with you can fuse carbon fiber into things, and it makes it lighter and it adds strength in certain situations. There's also wood infused, which is probably not useful for robotics, but it kind of can look like wood, especially if you put some finish on it. There's polycarb, there's ABS blend, that's something that we've used before. And there's this metal infused kiln product that, what's the name of the company? It's Proto Pasta from Vancouver, Washington. They make this stuff that you can print out. It's kind of a waxy material, but then they infuse in it a whole bunch of powder that's like a brass powder in this case. You can print it out this way out of the printer, and then you put it into a kiln in some plaster or some other kind of support material, and you melt off all of the waxy material, and it leaves the brassy look so that you can get kind of a metal finish. Turns out that it's fairly porous, and because it has all this stuff that it melted off, so the end result is kind of porous and brittle, so it's probably not super useful yet for FRC for strength or anything, but it is kind of a cool effect. So there may be some interesting things coming down the pipe eventually. So as far as what brand, I get people asking me a lot about what brand of filaments do I recommend. There's really kind of two ways to go. There's the brand specific, so whatever brand your printer is, usually it's been tuned, and the settings and whatever the default settings are tuned for their brand of filament if they sell a brand. So specifically for our team, we actually try to use Zortrax brand filament because it actually works better. It is more expensive. You can see it's not quite twice as much as like a generic, but it just works better. So when we print something with support, we can actually get the support material off, and it looks pretty good. The end result product looks good out of the printer. It looks better than if you use generic. And we find that it seems a little stronger, so we tend to buy the Zortrax printer filament instead of getting generic. It might cost a little bit more money, but we think the parts are better enough that it justifies it. We used to have a printer a long time ago. It's not working anymore, but it had you could only use printer filament from that company. It had like a little chip in it, and you had to sense that chip in order to make it use the filament, and that wasn't such a great success. Anyway, there's a lot of good generics out there. Hatchbox is a good one. Sunlu, I've heard a lot of people have success with. So there's a bunch of other ones if you want to go with generics, but you can also use brand specific. Strength and temperature properties. Those are some of the key pieces to choosing which type of plastic you use and some of the other things. But there's also some other properties that can go into that. So if you want to add some strength, there's clearly, impact resistance, stiffness I talked about earlier. You can change the type of plastic you're using, and you get a little bit different, right? If you go to ABS, you have more compliance, so it's a little bit better impact resistance, but it doesn't have as much stiffness as PLA. But one of the other key factors in 3D printed parts and FDM specifically is the direction that the grain is going, the directions of the layers. The layer adhesion, the adhesion between the different layers, is about half as strong as the strength, the stiffness from going with the layer. So in this case, right, if you're pulling apart this way, or if you're trying to have like a shear force that's trying to rip it down the middle, this is going to be much stronger than if you're pulling it apart where the layers can just separate, or if there's shear forces that go with the layers. So one of the really key things is if you have a directional forces on whatever your object is, pick the orientation that you print it based on what the forces are that it's going to face, so that the forces can go against the grains because it's going to be twice as strong approximately. That's one of the big things. So think about that when you're considering the orientation of printing as well, is that it really affects the strength. Other things you can do is you can add more wall layers. So usually there's like 2 or 3, maybe 4 wall layers at the outer dimensions, but you can add more and it gets stronger up to a point. And then also you can add infill. So generally speaking, it's 100% infill is actually less strong, depending on the measure of, exactly what kind of forces, but generally you're going to be better off with 70 or 80% infill of some kind, like a hex or a gyroid infill. Those are some of the strongest ones. That's going to be better than 100% infill. And the other things you can do to increase, if you really need to increase that layer adhesion strength, is you can disable the part cooling fan, and you can increase the extruder temperature. So increasing this extruder temperature means that you have more problems with drooping. So if you're bridging, you'll end up with a little bit more droop. But if your part doesn't have any bridging in it, then being able to print at a higher temperature ends up giving you a better layer adhesion because it melts the 2 layers together more. And not having the part cooling fan means that the previous layer is actually still warmer when you print over the top of it with the next layer, so that melts the plastic layers together better. And I get a lot of this information from a YouTube channel called CNC Kitchen, and he's got a lot of really good scientific studies on different strength properties, comparing different filaments and different ways of printing them, and getting the different layer adhesion versus across layer properties, things like that. And one of the things that I've heard people talk about recently, and he did a study on it, is if you anneal it afterwards, so you can reheat the part after it's been printed, you reheat it in an oven to where it gets to a melting point and it tries to melt the layers together. That's of course risky because now you're getting something so hot that it's going to droop and melt and change shape. But if you put it in plaster or in a bucket of salt or something, then that can possibly help. Anyway, it's interesting things to investigate, and you might check out his channel. It got a lot of good information. Another interesting technique I've seen is things where you insert something else into the 3D printing plastic. So I mentioned Markforged earlier, and they do have a very strong filament. Their filament is called Onyx, I think is their brand name. It's a nylon with carbon fiber infused. So you can see here, there's this kind of an interesting, complicated strength chart, and kind of getting both flexed strength, this is sort of your impact, and then strain. But you can see that Onyx is actually substantially better than ABS here, which is pretty good, and even nylon without the carbon fiber. So it's actually a really good filament just on its own. But then when you add one of their really interesting techniques, which I think you can mostly only get from Markforged, where they can take, after each layer, you can insert a single filament strand of something like carbon fiber or Kevlar. That provides you with even more strength. So you can see on this chart, this over here, now this is the Onyx, kind of more of the baseline, and then you add that fiber across there and you get even more strength. It's a very expensive technique and a very expensive printer, but it's one that a lot of the teams are using these days. It's a very cool one. I would like to have one of those printers myself. The other thing is a very similar technique is that I saw somebody trying to do where they took a steel cable and they designed their part to have a little channel through the middle of it, paused the print halfway through, ran the steel cable in, and then printed the rest of it, and that actually produced some interesting strength properties too. Feels like a lot of extra work for something that I look at and I think, well, maybe I should just design it out of metal to start with, but it's an interesting option. I don't know what else you might want to do. Maybe just some wire might be easier, but it's an interesting thing to consider. So what are some of the pitfalls in 3D printing that we've run into? So first off, just debugging printers and running into problems, I wanted to include kind of a picture and just sort of a basics of how they work, because then as you're trying to debug and figure out what's wrong, you might be able to just understand the mechanisms better. So really FDM printing is all about controlling the temperatures. So you can see here, this is a standard E3D V6 hot end. Not all printers use this, but a lot of printers do. And the key piece here is the red thing is the filament going through. You've got the heat sink up here, and the filament is going through this heat sink area, and it's close to where the heat is coming from, the print bed and the big heater here at the nozzle. So the heat tends to want to creep up this way, and you need to have this fan blowing across it and this heat sink to try to keep it cool, because the idea is you need this filament to not melt until it gets right down here, down at the nozzle. So you need to keep this cool up here, controlling the temperatures. And if you don't keep it cool enough up here, then heat will creep up here and it'll actually melt before it gets to the nozzle, and then the whole thing jams up and you have a problem, you have to debug. So then once it gets past that point, now is when you need to get it hot right here, and you need to get it to the right temperature right here to make a little puddle of molten plastic, so that as the filament goes through here and puts pressure on the molten plastic, it extrudes out the nozzle. And then more temperature control, you need to have like a part cooling fan, especially if you're using PLA, and maybe a heated print bed at the bottom. And having the heated print bed and the part cooling fan allows you to tune and adjust how the extruded plastic, how the part cools, because you don't want it to cool too fast. If it cools too fast, you get warpage, but if it gets too cold, then you have adhesion problems on the print bed. So everything is really about controlling the temperatures all the way up and down. That's why there's so many fans and heaters and temperature sensors and stuff on these. So again, more about temperature. If you're using PLA in particular, you really need to consider where you're using it. So this was an example of somebody who printed something, the same object in PLA and ABS and PETG, and then purposely left them on the dashboard in his car. You can see the PLA, it melted. The other two seem to be okay. The key here is you might be thinking, oh, well, I print PLA at 200 degrees C or 190 or 210 or whatever it is, right? 200 degrees Celsius is really hot. Your car doesn't get that hot. So why did it do this? Well, it's because that's the point, that's the temperature where it's really nice and fluid and it will flow well out of the nozzle. But there's a point much earlier called the glass point where the plastic just starts to get soft. And that's a lot cooler. And in fact, your car can get to that temperature, or even if you just set it outside in the sun, you can get that temperature and PLA will end up drooping. Which means that from a robotics perspective, you need to be careful where you put it. If you put it too close to a motor, especially if it's PLA, maybe one of your drive motors, maybe it gets really hot, you're gonna end up with lots of drooping and melting things, and you're gonna be, your amber light mount is gonna dip or something because you put it too close to something that's gonna get hot. So you wanna consider what type of plastic you use and where you're trying to put it. Also, impact zones. So this is an example on an intake where we had these nice little motors to try to protect the end caps area of 775. We went through one of these things every match, maybe two of them per match, because they just were in such an impact zone. They just got hit all the time. And we were printing in PLA at the time, and while it's nice and strong, it doesn't have very good impact resistance, so they were just always cracking and breaking. This also is PLA. This was a nice end cap on one of our robots on, yet again, an intake, and it got beat up pretty severely, as you can see here. So another thing to really consider when you're talking about 3D printing things is print time and how do you use your printer, right? It takes a long time. In this particular example, we designed up some really cool 3D printable amber light mounts. And you're like, wait, but this is metal. Yeah, it is. I'll get to that. So we had some really nice designs, and we would print them out. They would take, I don't know, an hour and a half or something to print out, and we had a couple of spares. But we go to competition, and people lean on it, it gets busted in competition, and then the amber light falls down, and you've got to figure out how to attach it. So we went through a lot of these. We kept revising the design, trying to make it a little bit stronger. We would print more of them, and then one day somebody came in and just said, well, I could just make that out of metal, and it would take me like 10 minutes. There's a piece of sheet metal bent in 90 and then 3 holes. It won't take me that long. And sure enough, he made one, and it was much better, and we used that one for the rest of the season. So there are times that whatever your usage is and whatever it is, maybe you're still better off doing it in metal instead of 3D printing it. As much as I like 3D printing, sometimes it's just not the right answer. So you have to think about that. So a tip that we've used, especially considering how long it does take to print things, and when you are, meeting in the evenings, and it takes, your meeting is only 2.5 hours or whatever, and it takes you 3 or 4 hours to print something, you really only get one print each day. You start one in the evening, and you don't get to pick it up until you get back to the lab, and you pull it off the printer, and then you can print another thing. So every day you only get one thing, every time you have a meeting. So in order to make sure that we have the right priorities and that we've coordinated with people and that we know what we're doing, we've created this spreadsheet on Google Drive that everybody can have access to, and they can put their parts up here, and then we discuss priorities, and we make sure that we're printing the first one. It also gives us the opportunity to make sure that they've located, we know where to find the CAD file, so that when the student is going to try to print it, they know where to find it. They know what material to use, right? A bunch of those questions. We found this to be much more useful than, I don't know, what we used to do, which was, I guess, somebody comes running in with a USB drive and says, print this. This is a much more organized way to approach it. It allows us to have multiple things in the queue and know which one is the most important to get done, and a bunch of the other information on it. So this is just what we found. I'm sure there's other ways to handle it. So let's talk about for robotics. What do you do with 3D printing for robotics? And we'll show some of the things that our team has used. So one of the first things we did with 3D printing was these intake rollers. We needed a fairly sized, big size diameter roller that was a pretty long design, and we were trying to figure out how to make it light. It needed to be light and fairly durable because it was on an intake, and intakes take a lot of beating. And so what we ended up doing was 3D printing these discs so that we could adjust to get the exact diameter that we wanted to design. So we 3D printed discs with a hex shaft hole in the middle, and then wrapped, so there's I think 3 discs here, one on each end and one in the middle, and then we wrapped it with a 1/32 polycard and then this tread, and then riveted it down to the 3D printed parts. And it turned out to be very light, very useful. It worked really well. It was nice and light, easy to move, easy to work on, move in and out, and it turned out to be a really nice design. Most of what we do with 3D printing is going to be the brackets and the mounts and those kinds of things. So here's a couple of encoders we've used. These are some absolute encoders we've used over the different years, and you can see you can kind of design. We have the students design up different things to mount for specific locations so that it can sit exactly in the center of a shaft somewhere that needs to rotate up or down or around or whatever we're doing with it. And we also use it for like camera mounts. So you can see over here was one that we designed up to use for, it was a year we were using like a Google Pixel phone, I think, for vision tracking. And then a couple of years ago we were using the Javoy, and somebody designed this thing up to have even a big mounting place on the front for the LED rings. And the other thing that we were able to do on this one, it was one of the weak points of the Javoy is the USB. It had, I think, mini USB connector on it, and it was fairly flaky, so sometimes it would move around or jiggle a little bit and disconnect the camera. So we were able to take and 3D print another mounting piece over the top of it so we could just lock it into place. Once we got it in a good spot and working, we could lock it in so that it didn't ever come disconnected. So other specialty parts that we print with these, in this particular year we had a big cable chain, and we had all sorts of interesting problems with the cable chain flopping around, and we were moving the elevator so fast that the inertia of the cable chain would take it way up high off of the bar. And so so somebody catted up these brackets to kind of hold the cable chain in place. And then also the same kind of thing happened with the cord that was used for it. So we have a cap over here. And then the lateral motions from the cable chain were causing us problems. So somebody designed up this little thing which had 3D printed ends on it to trap it, and we were able to put the cool robot name on it. So this is just a bunch of specialty parts, things that don't get as much impact, aren't next to hot stuff, but you need like something that curves like this and does a thing and wraps around to something, and that's where we end up using 3D printing a lot. And as I said earlier, under the OpenSCAD section, right, we use them for generating these custom designed pulleys, so you can get exactly the right number of teeth to get the ratio that you want, something that fits the shaft that you want, things like that. And you can see here, this one's out of the polycarb ABS blend, so it was actually really quite a strong one. So the nice thing is that hex shaft hole is really strong. And then over here, we printed one that was like super small that fit on a gray hill, so we could track the right amount of movement on this belt. This was for our turret, I think, in one of the years. Also, one of our other favorite things to do with 3D printing is this battery mount. So we have a way of mounting the battery where this battery mount, the little lumps on this battery mount, fit in the open on the top edge of the battery. So we set the battery down on its side over the top of this. So as long as the battery doesn't lift up, it's not going to go anywhere. It can't move laterally at all. And then we use a strap to hold the whole thing down so it can't lift up. So once you have the strap on, the battery is very secure, and this thing is bolted directly to the chassis, so nothing's moving. And it's just a simple 3D printed part, nice and light. We use it a lot for prototyping. This was from a couple summers ago. We did a version of the Mark II swerve setup from Jack in the Box, and the students changed a bunch of the CAD files, changed the dimensions, altered some stuff so we could 3D print things. And basically, we were able to buy some of the parts, like some of these gears here, but a lot of it we ended up 3D printing because we didn't have access to some of the other manufacturing at school, and we couldn't get the bevel gears because they're out of stock everywhere, and a bunch of other things. So we actually 3D printed the main pulley here. We 3D printed this base piece and even the bevel gears, and this is still working. I don't know that we would run it with bevel gears in a competition. This is just all done on PLA, and it probably isn't super strong, especially the bevel gears. I'm really surprised they haven't broken yet, but it seems to be holding up pretty well. So it's great for prototyping stuff. The other thing a lot of teams use it for, and we have done before too, is for awards and trophies and things you give out to your alliance partners or whatever. So here's a couple that we've done in some years. Dozer bought when the last year that Dozer was on there, and some other things. So Fred printed this one, gave it to us at some point during one of the competitions. It was cool. Some nice little awards and trophies. And here I would ask about what your team has done, but you can just tell me later offline if you want. But that's it. I hope everybody's enjoying the virtual First Fair, and thank you for listening.